Hello everyone, my name is Jingwei. I'm from China. I'm very pleased to be here to join the IC 2022. The topic of my presentation is bronchiectasis detection and classification based on deep learning. My speak will include these 6 parts. First is the introduction, and then introduce the data processing methods we use. The third part is deep learning models selection and improvement. The fourth part is experimental results and discussion. The fifth part is system implementation. Finally is a conclusion. First is the introduction. Bronchiectasis is a chronic condition where the walls of the bronchi are thickened from inflammation and infection. In 2016, a study conducted by McDonald in Europe showed that the prevalence of bronchiectasis had exceeded the prevalence of rare disease defined by the European Army of 5 in 10,000, and the prevalence and incidence showed an increasing trend year by year. It poses a serious threat to people's lives, study, and work. HRCT, high resolution CT, is a classical method for the diagnosis of bronchiectasis, but it cannot be widely used as a screening tool in the population due to its high radiation dose. Due to its low radiation, LDCT, low-dose CT, is widely used in physical examination and screening programs, and is a convenient, economical, and safe examination method. Object detection is a popular direction in computer vision and digital image processing. For some disease, the accuracy of AI diagnosis and analysis has reached the level of professional doctors. On this basis, we conducted a study on the diagnosis of bronchiectasis. The main contents of this study include data collection and label, data processing, experimental compression of deep learning model, improvement of deep learning model by using deleted convolution, and design of automatic scoring system based on scoring criteria, etc. The objective of this study is to develop a standardized intelligent detection, classification, and scoring system for bronchiectasis. Our research content mainly include 5 parts, as shown in the picture. First is the data storing and labeling. In this part, the CT images were collected and labeled to form a high-quality data set. The second part is image preprocessing. In this part, image preprocessing was used to enhance the experimental effect. The third part is model selection. We compared different deep learning model. The fourth part is model improvement. In this part, we improve the model to improve the effect. The fifth part is the automatic system. In this part, we realize the automation of the whole system process. In this study, deep learning was applied to the detection and severity classification of bronchiectasis, established a mapping between the original image data and the above bronchiectasis scoring system. Compared with human doctors, the model can process a large number of data at the same time quickly and efficiently, with the same judgment accuracy as human doctors. Doctors only need to judge the samples that the model is uncertain about, which significantly reduces the burden of doctors. 2. Data processing. Data collection. This study uses the datasets based on a study of medical groups, nationwide, large-scale LDCT screening programs. Low-dose scanning was used. These scanning parameters are as shown. Severity Classification. According to the lumen diameter and the ratio of adjacent vascular diameter bronchiectasis, severity can be divided into three kinds of severity and evaluation of 1 to 3 points: 1 mild, 2 medium, 3 severe. The pictures below shows the three kinds of bronchiectasis. Severity scoring rules. This study uses Riff and Briggs scoring criteria to score bronchiectasis. Riff is to classify the severity of bronchiectasis into 1, 2, and 3 points according to the rules, and scoring the 6 long lobes separately and add them together with a full score of 18 points. Briggs is to classify the severity of bronchiectasis into 1, 2, and 3 points, also according to the rules, and take the highest score of bronchiectasis in the whole lung as the final score. Data processing. First, we use pulmonary parenchymal segmentation. Lung parenchymal segmentation is to segment lung parenchymal from CT images, excluding areas of no interest, such as skeletal regions and external regions. In this study, the maximum interclass difference method was used. The pictures below shows the original image and the segmented image of lung parenchymal. Then we use lung lobe segmentation. In order to further improve the detection effects of deep learning model on bronchiectasis, we used a lung lobe segmentation method based on UNet-IDAD. UNet-IDAD improved on the basis of UNet by linking two adjacent nodes and adopting dense connection. In this study, UNet-IDAD was used to detect lung furrow and lung lobe segmentation. The pictures in middle is the original image and the lung furrow detection image. The picture below is the segmentation image of lung lobe. They are left upper lobe, left lower lobe, right upper lobe, and right lower lobe. 3. Deep learning model selection and improvement. With the continuous development and progress of medical imaging technology, computer technology and artificial intelligence technology combine, the combination of medical image analysis and deep learning has become an indispensable tool and technical means in medical research, clinical disease diagnosis, and treatment. AI-based medical image research focus on the analysis of various types of medical images. For some diseases, the accuracy of AI diagnosis and analysis has reached the level of professional doctors. At present, the mainstream deep learning algorithms are mainly divided into one-stage and two-stage. One-stage target detection algorithm is characterized by one step and only needs to be sent into the network once to predict all the binary boxes. The most typical one-stage detection algorithms are ULV5. Two-stage target detection algorithms such as FastRCNN algorithm will from candidate frames and then classify each candidate from and correct its position. This kind of algorithms is relatively slow because it requires multiple runs of the detection and classification process, but the detection accuracy is relatively high. Typical two-stage algorithms are FastRCNN and MaskRCNN. The deep learning methods based on the two algorithms have their own advantages and disadvantages, but they both achieve good performance in the field of target detection. MaskRCNN is developed on the basis of a fast RCN on which ROI elegant and fully convolutional network are added. Mask RCN spells classification prediction and mask prediction into two branches of the network. The classification prediction branch is the same as fast RCN, which gives prediction for the region of interest and generates category label and rectangular box candidate output. The mask RCN model structure shows in the picture. 4. Experimental results and discussion. Model contrast. First, we designed experiments to compare the classification effects of YOLO-V5 and mask RCN deep learning models. Other training parameters and test conditions remain the same. It can be seen from the figure that the mask RCN model is superior to YOLO-V5 in classification accuracy of the three categories. IOU calculates the ratio of intersection and earning of predict border and real border. The IOU mirrors the correlation between reality and prediction, and the higher the correlation, the higher the value. We compared the detection effects of two deep learning models, YOLO-V5 and mask RCN. It can be seen that the IOU of mask RCN is higher. That is, the correlation between mirrored reality and forecast is higher. Table below shows the AP50 and MAP50 of the two models and the three bronchiectasis categories. From the experimental results, we can see that the detection and classification effects of mask RCN is better than that of YOLO-V5. Next, we compared the detection and classification effects of mask RCN and mask RCN using deleted convolution. From the table, we can see the mean accuracy ratio of mask RCN at deleted convolution is higher than mask RCN only. And the IOU of mask RCN at deleted convolution is also higher than mask RCN only. Based on the above experiments, the method of deleted convolution can improve the detection and classification effects of the mask RCN model for bronchiectasis. Pictures below shows the effects of mask RCN for the actual detection of three types of bronchiectasis using deleted convolution. The detection rate can reach 91.0%. The classification accuracy can reach 92.2%, and the average detection time of a picture is only 0.9 seconds. Under the premise of high accuracy, it has a fast detection speed and a high reference value. 5. System implementation. In our study, Python was used to build an automatic segmentation and scoring system for bronchiectasis, which connected all the steps in series to realize the automation of the process. In other words, when the patient's CT image is available, the system can automatically perform the above series of operations, such as pre-processing, model segmentation, and scoring, and finally obtain the patient's bronchiectasis severity score. The system flow diagram as shown. As shown below, the specific process of Reef and Breaks automatic scoring system (RBASS) for bronchiectasis of CT images is as follows. The patient's CT image was put into the system. First, the required long CT image was extracted using field for format conversion and then the long pyrochromia segmentation based on the maximum difference method was performed, and then the long lobe segmentation was performed using unit add for detecting lung failure. Then the segmentation images of the lung was sent into the trained mask casting model with deleted convolution to obtain the bronchiectasis position and the score of each lung. Finally, the score of bronchiectasis severity was obtained by combining reef and Briggs score rules. For example, a CT image is divided into 4 lobes: upper left, lower left, upper right, and lower right. Among them, no bronchiectasis in the left upper lobe and bronchiectasis in the left lower lobe were classified as true, with a confidence probability of 98%, while no bronchiectasis in the right upper lobe and bronchiectasis in the right lower lobe were classified as true, with a confidence probability of 90%. Therefore, according to reef scoring rules and Briggs scoring rules, the final score of bronchiectasis severity of this image was reef 4 and Briggs 3. 6. Conclusion. In this study, the obtained data were screened and processed, and a highly quality long CT dataset was obtained to provide a basis for deep learning model training. Then the detection and classification effects of ULV5 and mask casting was compared, and the deleted convolution was used to improve mask casting and improve the experimental effects. Finally, an automatic reef and Briggs scoring system for bronchiectasis in CT images was designed in this experiment. RBASS, which couldn't only detect the position of bronchiectasis in LD CT images, but also obtain the severity scores of reef and Briggs bronchiectasis with high accuracy and fast detection speed. The study improved classification and detection accuracy compared with other using deep learning to diagnose bronchiectasis. The evaluation of the severity of bronchiectasis is more rigorous and convincing by judging the severity of bronchiectasis according to the authoritative scoring criteria. The study also designed and features an automated system that is user-friendly and easy to operate for both doctors and patients without relevant professional background. The evaluation result of the system can be used as a useful reference for doctors to identify bronchiectasis, which will not only enhance efficiency but also reduce the burden of doctors. Okay, my speaker ends here. That's all of my share. Thank you for listening.